welcome to the deep dive. You know, when we look up at the stars, especially the really distant ones, the light that finally reaches us isn't quite the same as when it started its journey.
Right. It gets dimmed, and it also appears redder.
Yeah, exactly, redder. And that's because of all the stuff between the star's dust and gas just floating out there in the interstellar medium.
Sort of like looking through smoke or haze.
Totally. But the Gaia Space Telescope, being up in space, it doesn't have to worry about Earth's atmosphere messing things up, which is a huge plus.
It gets a much clearer view of that interstellar haze. And this dimming and reddening, what we call interstellar extinction, it happens across the board color-wise.
But it's not just a smooth dimming, is it? There are specific details.
Precisely. If you look really closely at the star's spectrum, its rainbow of light, you see these distinct dips, specific wavelengths where the light is missing, like fingerprints.
Fingerprints. Okay. So they tell us what the light passed through.
They can, yeah. Some of these absorption features match up with things we know are out there, like water ice or silicate dust grains. You can see their signatures.
Gotcha. And that leads us to today's topic, right? These diffuse interstellar bands, or DIBs.
That's the one, DIBs. They're a whole set of these absorption dips, these fingerprints, that were spotted, believe it or not, over 100 years ago.
A century.
Yeah.
And we still don't know what causes them.
Largely no. It's one of astrophysics' big, long-standing mysteries. We see these features in the light from countless stars, but identifying the source, the material that's actually doing the absorbing, that's been incredibly difficult.
Why so tough? Don't they match anything?
Well, that's the core problem. Their wavelengths, where these dips appear, they just don't line up neatly with the known spectral lines of individual atoms or even simple molecules that we expect to find floating around in space.
Huh. So it's not just hydrogen or helium or something simple like that.
Yep. And another clue is that DIBs are generally broader, sort of smeared out, compared to the really sharp lines you get from single atoms in the interstellar gas.
Broader. Why would they be broader?
The thinking is it might be due to unresolved rotational structure. If the absorber is a molecule, it can rotate, and different parts of the rotating molecule might absorb slightly different wavelengths, blurring the feature out.
Okay, complex molecules maybe? But
Yeah.
even back in like the 90s, we didn't have much luck pinning them down.
Not really. There was a major review back in 1995 by Erbig, and out of about 127 confirmed DIBs known then, in the sort of visible and near-infrared part of the spectrum, there were only maybe 2 very tentative identifications, nothing solid.
Wow. And has that number 127 changed?
Oh, drastically. We're now looking at something like 600 known DIBs. They've been found all across the spectrum, ultraviolet, visible, infrared. The list just keeps growing.
600 mystery fingerprints. So what were the early ideas? You mentioned dust earlier.
Yeah, for a while, interstellar dust grains were a prime suspect. Because, well, generally, the more dust you look through, the more reddened the star appears, the stronger the DIBs tend to be.
Okay, that seems logical. More dust, stronger signal.
It does, but the details didn't quite fit. The current favor theory, the one with the most traction, is that DIBs are caused by various kinds of free-floating polyatomic molecules.
Polyatomic, so molecules made of many atoms.
Exactly. Big, complex ones. Things like polycyclic aromatic hydrocarbons, PAHs, kind of like complex soot molecules or other large carbon-based molecules, maybe even carrying an electric charge, just drifting in space.
So not the solid grains themselves, but maybe complex stuff associated with dusty regions.
That seems more likely. And we actually have one solid identification now, which was a huge deal.
Oh yeah. What did we find?
5 specific DIBs in the near-infrared have been securely matched to ionized Buckminster fullerene, C60 plus day.
Buckyballs. That's soccer ball molecules.
The very same, just with an electron knocked off, giving them a positive charge. Finding charged buckyballs floating between the stars, absorbing light at those specific wavelengths, that was a major breakthrough.
Okay, so one confirmed carrier, C60 plus A, responsible for 5 DIBs. But there are hundreds more DIBs. What's the holdup with the others?
Well, a really key puzzle is that the strengths of most DIBs don't seem to be strongly correlated with each other.
Meaning?
Meaning, if you look at 2 different DIBs in the light from many different stars, you don't necessarily see them both getting stronger or weaker together in lockstep.
So if one molecule caused, say, 10 different DIBs, you'd expect those 10 DIBs to always vary in strength together, right?
Exactly. The fact that they don't strongly correlate suggests it's not one single type of molecule causing all, or even most of them. It points towards a whole population, maybe a whole family, of different carrier molecules out there, each responsible for its own set of DIBs.
The whole zoo of interstellar molecules causing these things.
Could be. And it's still interesting that despite this lack of correlation between individual DIBs, their overall strength does tend to track with general interstellar extinction, even if dust grains themselves aren't the direct carriers. The relationship is there, but it's complex.
Okay, so a big complex mystery, lots of different molecules likely involved. How does Gaia, our galaxy mapping mission, fit into cracking this?
Well, Gaia's contribution is actually really significant here, especially through one of its instruments, the radial velocity spectrometer, or RVS.
What's special about the RVS for this?
The wavelength range, it observes a specific slice of the near-infrared spectrum between 845 and 872 nanometers, was chosen partly because it contains a known DIB.
Convenient. Which one?
It's a medium-strength DIB centered around 862 nanometers. It was first identified back in 1975, and even back then, people noticed it seemed to correlate pretty well with interstellar extinction.
So the idea was maybe this particular DIB could be used as a tracer.
Precisely. The hope was that by measuring the strength of this 862 nanometer DIB in millions of stars, Gaia could help build really detailed maps of interstellar material, especially in areas where there's a lot of it.
And Gaia is measuring this.
Oh, yes. There's a whole part of the Gaia data processing pipeline, the GSP spec module, dedicated to analyzing this DIB in the RVS spectra. For vast numbers of stars, it calculates the DIB's equivalent width. That's basically a measure of its strength, how much light it removes.
Okay.
Its precise central wavelength, its width, and it gives quality flags, too. It's generating this huge uniform data set specifically on this one DIB.
A massive, consistent survey of one DIB across the sky. Has anyone started using this data?
Absolutely. One of the first really big studies using this data from Gaia's Data Release 3 came out recently, led by Schultheis and colleagues.
And what did they find? What does this massive DIB map look like?
Well, they ended up with a sample of nearly 500,000 stars with good DIB measurements.
Yeah.
And a high-quality subset of over 140,000. That's like 10 times bigger than any previous DIB study.
Wow, okay. That's a lot of stars.
It really is. And as you'd expect, when you map where these stars are, they're heavily concentrated towards the plane of the Milky Way galaxy. That's where most of the action is, interstellar medium-wise.
Makes sense. But you said substructure.
Yes. They didn't just see a smooth band. They plotted the data in clever ways using things called keel diagrams. They're a bit like Hertzsprung-Russell diagrams showing stellar properties.
Okay.
And they color-coded these diagrams based on the strength of the 862 millimeter DIB. Then they did it again, color-coding by the star's distance. And the patterns looked remarkably similar.
Similar how?
Stars that were farther away consistently showed stronger 862 millimeter DIB absorption.
Right. More distance means the light travels through more stuff,
Mm-hmm.
so the DIB gets stronger. That tracks.
Exactly. But the really cool part was when they focused on certain types of stars, massive bright stars at distances of about, say, 6,000 to 13,000 light years.
Okay, what about them?
Those distances place them right in the nearby spiral arms of our galaxy. The Sagittarius Carina arm, our own local arm, the Perseus arm. And guess what? Stars in those arms showed significantly stronger DIBs.
So the DIB is actually highlighting the spiral arm.
It seems to be an excellent tracer for them, yes. It's helping us map out the structure of our own galactic neighborhood in a new way.
That's fantastic. A side benefit almost. Did they compare this DIB strength to the general reddening Gaia measures?
They did. They looked at the reddening derived from Gaia's BP and RP photometers, this eBPRP value. And generally, there's a good correlation. Both the DIB strength and the reddening are higher in the galactic plane.
Which makes sense if they're both related to interstellar material.
Right, but they also found some really interesting differences.
Oh, like what?
For R, the material carrying this 862 millimeter DIB seems to hug the galactic plane more tightly than the dust does. It has a smaller scale height.
Smaller scale height. Meaning it's like a thinner layer compared to the dust layer.
Exactly. Think of the DIB carrier distribution as a thin crepe, while the dust is maybe a slightly fluffier pancake.
Okay, interesting distinction. Anything else?
Yes, and this is perhaps even more striking. They found evidence for the 862 millimeter DIB carrier inside the local bubble.
The local bubble. But isn't that supposed to be mostly empty, especially of dust?
That's the remarkable thing. It's a region around the sun known to be practically dust-free, yet the carrier for this DIB seems to be present there.
Whoa. So the DIB carrier exists where dust doesn't. That really separates it from dust, doesn't it?
It certainly suggests they aren't perfectly coupled. Maybe the DIB molecule survives conditions where dust grains are destroyed, or vice versa, or they're just formed in different places or processes. It's a strong hint they're not the same thing.
So how do they model this distribution then, this thin layer that's even in the bubble?
Well, as a first step, they found its spatial distribution can be reasonably well described by a simple SLAP model. Based on that, they estimated the local density of the DIB carrier near the sun and its scale height.
And the numbers were?
They got a local density equivalent to about 0.019 nanometers of equivalent width per kiloparsec of distance, and a scale height of roughly 99 parsecs. Plus or minus some uncertainty, of course.
So about 100 parsecs thick, that layer. Definitely thinner than the dust layer, which is typically a few hundred parsecs, right?
Correct. It really reinforces that picture of it being more concentrated towards the absolute middle of the galactic plane.
And Gaia also nailed down the exact wavelength.
Yes, with incredible precision. By looking towards the galactic anticenter, the direction opposite the galaxy's core, where things are a bit simpler motion-wise, they determined the rest wavelength of this DIB to be 862.086 nanometers, with an uncertainty of just 0.00019 millimeter, the most precise measurement yet.
Okay, and why is having that precise wavelength useful?
Because it allows you to measure the DIB's Doppler shift very accurately as you look in different directions across the galaxy. You can see how fast the DIB carrying material is moving towards or away from us.
Oh, mapping the gas flow using the DIB.
Kind of. They compared the velocities derived from the 862 nanometer DIB shifts with the velocities of carbon monoxide, CO gas, which we know traces molecular clouds.
Did they match?
Within about 1 or 2 kiloparsecs from the sun, so in our local neighborhood, the agreement was remarkable. The DIB velocities tracked the CO gas velocities very closely, following the pattern of galactic rotation.
So the DIB carrier is moving along with the known interstellar gas clouds.
It strongly suggests that, yes. Which lends more weight to the idea that the carrier isn't dust grains, but maybe these large gas phase macromolecules moving along with the general flow of gas in the galaxy.
Fascinating. Really builds a picture. Was this 862 nanometer DIB the only one Gaia's RVS could see?
It's the most prominent one in that range, but astronomers had previously suspected there might be another much weaker DIB nearby at around 864.8 nanometers.
Okay, a faint cousin.
Something like that. And more recent work, also using Gaia DR3 spectra, thousands of them actually confirm that this 864.8 nanometer feature is a real DIB.
They found it. How does it relate to the main one at 862?
Interestingly, its strength seems to correlate pretty well with the strength of the 862 nanometer DIB. When one is strong, the other tends to be strong too.
Which might suggest they have related origins, or at least hang out in similar places.
It could, yeah. It adds another piece to the puzzle. Although, it's also worth noting that the main 862 nanometer DIB still shows a better overall correlation with the general interstellar reddening, the eBPRP value, than this weaker 864.8 nanometer one does.
So they're linked, but maybe not perfectly. More complexity.
Exactly. It just underlines that the DIB phenomenon is intricate. Different DIBs, even ones close in wavelength, might trace slightly different conditions or components of the interstellar medium.
It's just amazing. We started with these mysterious dark lines in starlight over a century ago, and now Gaia is giving us this incredibly detailed map of one of them, revealing galactic structure and hinting at the very nature of the molecules causing them.
It really is a huge leap forward. The diffuse interstellar bands are still fundamentally mysterious in many ways, but Gaia's data, especially for the 862 millimeter DIB, has provided an unprecedented view.
Yeah, seeing how it traces spiral arms, how its distribution is different from dust thinner, present in the local bubble, and how its velocity matches the gas. It's painting a much clearer picture.
Definitely. And finding that weaker cousin DIB nearby and seeing how it correlates just adds more depth. We're moving from just cataloging DIBs to really probing their behavior and environment across the galaxy.
Absolutely. It really leaves you wondering, doesn't it? With hundreds of these DIBs still unidentified, scattered across the spectrum, just imagine what other complex molecules might be out there hiding in the interstellar shadows. What else are they telling us, subtly, through these faint absorptions in starlight about how galaxies evolve? Or even about the raw ingredients available for making future planets? It's quite a thought.